Today we're going to spend some time talking about mole ratios in chemical reactions. And we get mole ratios from balanced equations. So the first thing that I want to do is review why we balance equations. So we balance equations so that we satisfy the law of conservation of mass. So the law of conservation of mass tells us that, and you probably learned this back in middle school or even maybe back in elementary school, just basically says that matter cannot be created or destroyed in a chemical reaction. So if we have a reaction with silver and sulfur to make silver sulfide, then we know that any silver or sulfur that goes into the reaction in terms of mass has to come out on the other side. So when we have a balanced equation, we can add up the mass of our reactants. That would be the mass of 2 silvers plus the mass of 1 sulfur. Okay, and then that should equal the mass of our products. So since we also have 2 silvers and 1 sulfur on the product side, then these two quantities are equal. And that gives us a valid chemical reaction. It tells us what goes in order to get the product on the other side. And so this is similar to a recipe in a lot of senses. And I've mentioned before the simple cheese sandwich equation. 1 slice of cheese plus 2 slices of bread gives 1 cheese sandwich. All right, and that is our balanced chemical equation for that particular process. Okay, it's not helpful to say that you add cheese plus bread and get a sandwich. You need to know how much of each of those things go in order to get the sandwich out on the other side. All right, and one thing we can get from this equation that we haven't yet used, although we did a little bit in the s'mores activity, is to use the coefficients to tell us the ratio of different ingredients to each other. So for every slice of cheese that we have, we need 2 slices of bread. And that ratio is called a mol-mol ratio or mol-mol factor. Okay, and you can do it with any of the quantities in the balanced equation. So 1 slice of cheese is also equivalent to 1 sandwich. And for every sandwich you make, you need 2 slices of bread. All of those are mol-mol ratios. All right, and it carries through that if 1 slice of cheese is 2 slices of bread, that 1 dozen slices of cheese would necessitate 2 dozen slices of bread, or 1 mole of cheese would necessitate 2 moles of bread. All right, and so now if we go on to using this in a chemical equation, which always seems to be just a little bit trickier, then we look at the ratio of iron to sulfur here in this chemical reaction. So we have 2 irons plus 3 sulfurs gives Fe2S3, which is iron 3 sulfide. All right, so we can tell from that equation that for every 2 irons, we need 3 sulfurs. All right, that is our mol-mol ratio for iron to sulfur, and that also works for 2 moles of iron equals 3 moles of sulfur. So those two things can be written as a ratio, either with iron on the top or on the bottom. It doesn't matter. All right, and we can do the same thing for how much iron we use to get a particular amount of product. So for every 2 irons that we use up, we get 1 formula unit of iron sulfide. So now we can take these mole factors and use them in chemistry problems. So if we want to know how many moles of sulfur are needed to react with 1.42 moles of iron, we can go back to our balanced equation. So if this had told us that how many moles of sulfur do we need to react with the 2 moles of iron, we should know from the ratio we just did that that would be 3 moles of sulfur. Right? But when we're given a decimal, like 1.42 moles of iron, it's harder to do that in your head. And so we're going to use dimensional analysis that we used in the previous chapters. So we start with what we're given, which is 1.42 moles of iron. And then we're going to use our mol-mol ratio in our parentheses. And so we want moles of iron to be on the bottom, because that's what we want to cancel out. And what we're looking for is moles of sulfur, so that's going to be in the top. So we just did on the previous page, for every 2 moles of iron, we need 3 moles of sulfur, and so that gives us 2.13 moles of sulfur when we multiply that out. Okay, and we can do this going from reactants to products as well. So how many moles of iron 3 sulfide can we make from 1.42 moles of iron? So again, we want to put 1.42 moles of iron in the front, and then in our parentheses, we're going to use our mole ratio. So for every 2 moles of iron, we make 1 mole of Fe2S3, right? And so that's going to mean that 1.42 moles of iron will give us 0.71 moles of iron sulfide. Now we're going to combine some factors or some skills that we've used in the past with what we just learned. And so there may be problems where you're given grams of a particular product or reactant and you want to find grams of a different one. Okay, and so what we now have the skills to do is to go from grams of A to moles of A, which is what we have done in the past, and we can get from moles of B to grams of B. And now, using our mol-mol factor, we can get from moles of A to moles of B. So this allows us to go to grams of one thing, go from grams of one thing to grams of another thing. So an example of that is here. So if we have N2 plus O2 gives 2NO, and we want to know how many grams of NO can we produce when we have 12.5 grams of O2 react. So the first thing that we need to do is figure out the molar masses of both O2, which is what we're given in the problem, and NO, which is what we're trying to find. So the molar mass of O2 is going to be 16 times 2, which is 32 grams per mole. And the mass of NO is going to be 16 plus 14.01, which is the mass of nitrogen, and that's going to give us 30.01 grams per mole for NO. All right, so the mol-mol factor for NO and O2 is going to be the ratio of those two things in our chemical equation. So every time we use up one O2, we get two NOs out of the reaction. So our ratio is going to be 2 to 1, 2 NOs for every one O2. Okay, and then we could use all of this information to get from point A to point B. So now to do the reaction, we're going to take what we're given, which is 12.5 grams of O2, and then we're going to first convert that to moles of O2. So we know that there are 32 grams of O2 in 1 mole, and we want grams on the bottom so it cancels. And then use our mole-mole ratio to get from moles of O2 to moles of NO, which is what we're interested in this problem. So we know that 1 mole of O2 can make 2 moles of NO. Again, we want moles of O2 on the bottom so that it cancels. And then the last thing we want to do is convert to grams of NO, which is what our problem asks for. So we know 1 mole of NO is 30.01 grams of NO, and that's going to go on the top because grams of NO is where we're going. All right, and then if we multiply and divide all of this out, we get 23.4 grams of NO. Now we'll just do one more example to practice. All right, and we'll do more of these in class than online in Mastering Chemistry. So in this example, we have a combustion reaction. We have heptane reacting with oxygen gas to make carbon dioxide and water. And the question is, how many grams of O2 are required to react with 22.5 grams of heptane? And so first we need to get molar masses for each of those things because we're going from grams to moles to moles to grams. All right, so the molar mass of heptane comes out to be 100.205 grams. And the molar mass of oxygen is 32.00 grams. Okay, and then we're going to start with what we know, which is 22.5, or what we're given, which is 22.5 grams of heptane. And the first thing we want to do is convert that to moles. So 1 mole of heptane is 100.205 grams. Okay, and we want the grams in the bottom so they cancel. All right, and the next thing we need is the mole ratio. So we know that for every 1 mole of heptane, because that's the coefficient up here, we need 11 moles of oxygen gas, because that's our coefficient here. Don't be afraid if the coefficients are bigger than 1 or 2 or 3, right? Sometimes that happens. Okay, so we want the moles of heptane on the bottom and the moles of oxygen on the top, and then we're going to now we're to moles of oxygen. The last thing we need to do is go to grams of oxygen. So we know that 1 mole of O2 is 32 grams of O2. Okay, now we have our whole problem set up. We just need to multiply and divide through, and that gives us 79.04 grams of O2. All right, so this wraps up our introduction to calculations using mole-mole ratios. We're going to do lots of practice with this, and you're going to get really good at it.